All right, let me quickly calibrate the room. Who here can raise their hands? Please raise your hand. All right, thank you. Who cannot raise their hand? Please raise your hand. Yeah, there's always one. There's always one. All right, but more seriously, who is relatively new to Kubernetes? All right, who is relatively experienced? And who confidently uses Kubernetes services today? And who confidently understands Kubernetes services today? Oh, wow, okay, that is, I did not expect that. Actually, I did not expect that. But so when we talk about cloud-native systems, we talk a lot about microservices, or services for short, right? And in that conversation, a service is an active component of the overall application. An active component that provides part of the functionality. So simply put, a service is something that runs. But then, sooner or later, we realize a Kubernetes service is not something that runs. Well, what is it? Over time, we build an intuition. After all, we have other things to worry about, and there is probably a Helm chart somewhere that does the trick anyways. So, well, today, let's try to replace that intuition with a solid understanding. But before we explore the question, what is a Kubernetes service, let's explore the question, what is a service? I'm going to use two different computational models, mental models, to reason about services. The first one, from an application developer's point of view, the world is simple. A distributed system is composed of a set of concurrent processes. Processes communicate by exchanging messages. From this point of view, a service is an active component, a process that offers some desired functionality. In that diagram, that functionality is represented by the blue dot. So that leads to the following definition. From the application developer's perspective, a service is any process that offers a desired functionality. But from an application operator's point of view, the world is more complex. Again, a distributed system is composed of a set of concurrent processes. And again, processes communicate by exchanging messages. However, here, indirectly, via a network. In the context of this presentation, we are interested in two different types of events. A process may send a message, and a process may receive a message. A message identifies, carries, both the source process and the destination process. So if we observe a send event at process 1, and the destination of the message is process 4, we will subsequently observe a receive event of that message as process 4. And similarly, if we observe a send event at process 1 and the destination of the message is process 5, we will observe a receive event of that message at process 5. This model, a model of concurrent, indirectly communicating processes, is not capable to express the idea of services. To do so, we have to make a few alterations. First, we need to introduce a new concept. Unsurprisingly, the concept of services. Here, service 1. Second, we have to introduce a new relationship, membership. In this example, process 4, 5, and 6 are all members of service 1. And third, the destination of a message may now either be a process or a service. If we observe a send event and the destination of a message is a service, the contract now states that we will observe a receive event at some process that is a member of this service. Here, if we observe a send event at process 1 and the destination of the message is service 1, we may observe a receive event at process 4. Or, if we observe another event at process 1 and the destination of the message is once again service 1, we may observe a receive event at process 5. So that leads to the following definition. From the application operator's perspective, a service is an anycast domain, a one-to-one out of many relationship, where a message sent to the service is received by any member of the service. So at this point, we identified and addressed a major source of confusion and contention. Is a service something that runs or something that doesn't run? And the answer is, well, it depends. It depends on how we look at it. From the point of view of the application developer, depicted on the left, a service is something that runs. It's a process. From the point of view of the application operator, a service is something that doesn't run. It's an anycast domain. The rest of this presentation deals with how Kubernetes implements services as depicted on the right. A Kubernetes service is not a process. A Kubernetes service is an anycast domain. So now we have everything we need to explore Kubernetes services. Wait. Here we go. We need a way to state the existence of a service. Spoiler alert, Kubernetes service objects. We need a way to specify the members of a service. Spoiler alert, label selectors. We need a way to destine a message to a service. Again, spoiler alert, a service gets a unique IP address. And we need a way to deliver a message to a service, that is, to deliver the message to a member of that service. Last spoiler alert, network address translation. But before we dive into the specifics, we'll briefly review Kubernetes architecture and Kubernetes network architecture. This diagram depicts Kubernetes architecture. The Kubernetes API server processes read, as well as create, update, and delete requests, and persists Kubernetes object in the Kubernetes object store. A core controller, depicted on the left, is any controller that interacts only with the API server, reading and writing Kubernetes objects via the Kubernetes API. Typical example for a core controller is a replica set controller. It reads replica set objects and writes pod objects. An edge controller, depicted on the right, is any controller that interacts with the API server and with other components. An example is a kubelet. It reads pod objects and instructs the container engine via the container runtime interface to execute init and main containers. To understand Kubernetes services end-to-end, we have to consider the Kubernetes API, 3 different Kubernetes objects, pod objects, service objects, and endpoint objects, a core controller, the endpoints controller, an edge controller, the KubeProxy, and finally, Linux net filter framework, specifically network address translation. Now to my least favorite part, networking. No, wait, I work at Cisco. Now to my favorite part, networking. This diagram depicts Kubernetes network architecture. Kubernetes defines 3 distinct networks: the node network, the pod network, and the service network. The node network consists of 1 address space. Each node of the cluster has an IP address from this address space. The pod network consists of multiple address spaces, 1 per node. Each pod of the cluster has an IP address from the address space of the node the pod is running on. The service network, again, consists of 1 address space, and each Kubernetes service of the cluster has an IP address from this address space. Okay, finally, we get to deep dive into Kubernetes services themselves. We will not focus here on the actual YAML or JSON representation. Instead, we will focus on a conceptual graphical representation and try to get the idea across. When a user creates a service, the user has to specify a service type. The service type is either cluster IP or node port. A service of type cluster IP is reachable from within the Kubernetes cluster. A service of type node port is reachable from within and from the outside of Kubernetes cluster. So therefore, cluster IP services and node port IP services are not in fact disjoint sets, but every node port service is also a cluster IP service. So to put it simple, node port adds a little bit to cluster IP. On creation, the API server, actually the API server, not an admission controller, the API server, assigns a cluster IP, a unique IP from the Kubernetes service network to the service object. But service objects do not exist in isolation. They are nested between pod objects and endpoint objects. Pod objects are the members of the service. A pod is a member of a service if the services selector matches the pod's labels, and the pod's readiness probe indicates that the pod is ready to receive traffic. If the pod does not specify a readiness probe, the pod is considered ready if it is alive. And if the pod does not specify a liveness probe, it is considered alive if at least one of the pod's main containers is up and running. The endpoints object is a materialized view of the members of the service. Conceptually, the endpoints object is like a lookup table that maps the service's cluster IP to the members' pod's pod IP, and the service's ports to the pod's ports. If the service is of type cluster IP or node IP, conceptually the endpoints object acts as a lookup table just like this. In this example, the service cluster IP and the service port 80 is mapped to any of these pod IPs and the port 8080. And similar, the service port 443 is mapped to the pod port 8443. In addition, if the service is of type node port, conceptually, the endpoints object acts as an additional lookup table just like this. In this example, on each node of the cluster, the node IP and port 32501 is mapped to any pod IP and the pod port 8080. And similar, the node port 32502 is mapped to pod port 8443. The node port values are either user specified or Kubernetes assigned. But now who makes all of this happen? Please meet the endpoints controller and the KubeProxy. The endpoints controller continuously scans for services and for pods that match the selector of these services and are in a ready state. It then updates the endpoints objects accordingly. On each node of the cluster, the KubeProxy reads the service objects and the endpoints objects to install the appropriate network address translation rules. So finally, network address translation rules are responsible to route messages that are destined to a service to any pod that is a member of this service. So, to reiterate, the KubeProxy is an edge controller that runs on every node of the cluster, reads service and endpoints objects, and installs network address translation rules. And network address translation rules are capable to change source address and source port, or destination address and destination ports of an IP packet. That kind of sounds like it has everything we need. This diagram depicts a Linux network stack, or more specifically, Linux netfilter. Netfilter is a set of hooks inside the Linux kernel that allows kernel modules to register callback functions with the network stack. A registered callback function is then called back for every packet that traverses the respective hook within the network stack. Pre-routing, output, and post-routing are hooks that are relevant for network address translation. But only pre-routing and output hooks are relevant for Kubernetes service network address translation. When a pod, here the process on the right, sends a message with a destination address of a service's cluster IP, the output chain will rewrite the destination address to a member pod of the service before the packet even leaves the node. And when a node receives a message via its interface, depicted on the left, with its node IP, and the message has a destination port that matches a node port, the pre-routing chain will rewrite the destination address to a member pod of the service and either deliver the message locally if the pod happens to be on that node, or forward the message. The pre-routing chain and output chain both jump to a Kubernetes service chain. For each service in the Kubernetes cluster, a service-specific chain rewrites the cluster IP of the service to one member pod IP with equal probability, making sure that a message destined to a service will be received by a member pod of that service. And with that, we close the loop and are true to our previous definition. But fun part. When does Kubernetes service not work? Even so, Kubernetes is working correctly, so no single component of Kubernetes is in a failure state. For this example, we assume a Kubernetes cluster with two nodes, N1 and N2. We assume one service and two pods as its members, P1 and P2. Initially, pod 1, pod 2 are alive, healthy, and ready. Both P1 and P2 are listed as endpoints in the endpoints object. And network address translation will route requests to either P1 or P2 on either node, N1 or N2. Kubernetes is in a steady state. Requests reach their destination. But next, P1 fails its readiness probe. It is not ready to serve traffic anymore. However, both P1 and P2 are still listed as endpoints in the endpoint object. And network address translation will still route requests to either P1 or P2 on either node, N1 or N2. Now, per request, there is a 50% chance of failure, just because Kubernetes hasn't caught up yet. Next, the endpoints controller removes P1 from the endpoints object. However, network address translation will still route requests to either P1 or P2 on either node, N1 or N2. Still, per request, there is a 50% chance of failure. Kubernetes simply still didn't catch up yet. Next, the KubeProxy on either N1 or N2 will remove its network address translation to P1. Now, per request, there is only a 25% chance of failure. Kubernetes still didn't fully catch up. But finally, the KubeProxy on the other node will remove its network address translation to P1. Kubernetes is in a steady state. It is caught up. There is no failure happening. Now, fun question. Last but not least, how can we possibly mitigate this situation? If you take anything away from this presentation, this one sentence. In the era of desktop computing, there was no problem that could not be fixed by a restart. And in the era of cloud native, there is no problem that cannot be fixed by a retry. And this is where service meshes, and actually Andrew, enter the picture.
Thanks again, everyone, for staying till the very end of the conference to come to our talk. So Dominik and I have been talking about what our next talk is going to be about. So we need your help to kind of make this decision. So the two options are, one, inside service mesh, and where we talk about service meshes based on conceptual and formal models similar to this presentation. And then option two is the almost unbreakable microservice, which is if you want to learn more about how to compose services together with various CNCF projects into an almost unbreakable microservice. Okay, so for those of you who are interested in inside service mesh, show me some hands. Okay, awesome. And then for those of you who are interested in the almost unbreakable microservice, show me your hands. And I can't tell.
Same. But I think the unbreakable microservice almost has it.
Okay. So so I think we'll go with that. And with that, let's see. Are there any questions?
So I do realize one just come into my mind when I saw this one. So when you create a service, right, you specify the service IP address and the port number. And you deploy the service with multiple endpoints. What about the service port is conflict with a particular load? Do we take care of that one? Did you get that?
So generally, one additional point we skipped is that it is recommended that you use named ports. So for the pods, you would typically not specify the port. You use name ports. And with name ports, you let Kubernetes choose ports and then also the port mappings as much as possible. So in order to reduce conflicts. But of course, you are correct. Conflicts are possible.
Just want to ask, we have a special use case. We want to broadcast our message to a specific service. Just wondering if there's any model like that, instead of just iterating through the IP table. Thanks.
So no, the semantic of Kubernetes services is fixed. Any member will respond to a request with equal probability. You can, of course, slice and dice if you want to target a pod specifically. You can slice and dice. A pod can be a member of multiple services. Or if you want to get more capabilities into the hand of the application operator and application developer, you can resort to one of the service meshes, like, for example, Linkerd, where you have more capability of actually influencing the routing. But Kubernetes routing is fixed.
So as I was watching the presentation, I started to get lost around the endpoint part of it. It seemed like the endpoint was what was doing the service job, like it went and talked to all the pods individually. Could you just talk a little bit more about that part? I really got lost in that area.
Oh yeah, absolutely. So the endpoints object is really just the materialization of the list of pods that are the members for the service. So you could think of it as a database materialized view, because otherwise it is just too costly for Kubernetes to actually recalculate which pods match the services selector each and every time. So there is an endpoints controller that does this specific part centrally and uses the endpoints object to materialize that information. It is simply a list of pods that match the services selector.
Thank you for the talk. I was wondering, for the network address translation, if those rules are run for every packet, how do you ensure that all the packets on a single connection go to the same endpoint? Does that make sense?
Yes, that is, now this is far out of my comfort zone, but network address translation actually has something that is contract tracking. So it does, on a level 4, it actually does track the session of the TCP connection. But that's actually far out of my comfort zone.
So can you talk a little bit about how cluster IP none works?
Cluster IP none, the
Like-
external services, we gotta exclude that. It's also out of my comfort zone.
So my understanding, there is no additional network hop from what you explained. Is there sometimes a circumstance when service represents an additional network hop?
I'm sorry, if what?
Just my understanding, there is no additional network hop. So basically, you connect from the client directly to the pod. It's just a lookup table. Is there, I don't know, some setup when a service is representing an additional network hop and associated overhead?
With IP tables, I do believe no, whereas the specifics are, the devils are in the detail. In that case, the detail is container network interface, but the CNI, yes. But in any case, no, it should not. If the KubeProxy mode is actually user space, then the KubeProxy is indeed a reverse proxy. Then you have an additional network hop. And if the packets come from the outside, they may be routed to any, so node port, they may be routed to any node, typically in a round-robin fashion. So then there is, again, an additional network hop if the target pod is not on the node that the packet went in initially. But typically, no. The idea is no. If there are no other questions, thank you very much. Thanks for staying that long.
Thank you, everyone.